See this? In this paper, let's discuss about the structural isomerism and tautomerism questions. The first one, which of the following is predominantly going to exist in enol? So basically, you need to make an enol and see whether it will exhibit some stability. Now, the problem in the first case is due to the strong repulsions between the lone pairs here, they would always try to exhibit in the anti-form. So that's why it will not undergo enolization that easily. So that means if you want to get this kind of enolization, it is impossible. Okay. In fact, 100% of it would exist only in keto form. Hardly anything will be existing in enol form. Second, here there is sufficient amount of enol content because of extended conjugation. Like this, you can see from this lone pair, it can push here, the pi bond can move here, this can move here. Extended conjugation as well as hydrogen bonding, it will support immensely. Third case, if you notice, we have double bond O, and here, so in case if at all I make an enol form on this particular space, here there is again an extended conjugation, but problem here is this lone pair is already helping in making the resonance stabilization done. Got it? Because of which the extent of hydrogen bonding is extent of conjugation is weaker. So that means even though it want to make the resonance, this side the resonance will be weaker. And because these are esters anyway, esters will have least amount of enol formation. Okay. So in fact, if you notice the percentage wise, the 2 keto part will always have percentage of around 80, 78, 76 percentage enol. This would be around 8% enol. And this will be around 10 raised to power of minus 3% enol. Okay. Hence, predominantly the most enol content is observed in B. Okay. Next. Total number of possible cyclic isomers here. Okay, so let's see what are all the possible isomers in this case. Cyclic isomers of C5H10. So as per the question, you can clearly make out that the degree of unsaturation is 1. So we start with the 5-membered ring like this, 1, and then with 4-membered ring like this, 3-membered ring, we can have an ethyl here, we can have 2 methyls here, we can have 2 methyls separated this way. Okay, these are the forms which we have, correct? Since here he didn't specify about uh, I didn't specify about stereoisomers, correct? You always take it as a total. That means structural plus stereo, correct? I should have mentioned it as structural here because we were discussing more of a structural kind. Uh, but usually the questions, if at all it comes over like this, it is always meant to be with stereo. Anyways, notice that here we have cyclic ones if you compare. So 1, 2, 3, 4, 5. These are the 5 cyclic based structures we have. And in here, this is the place where there are chiral centers here, correct? But in these chiral centers, you will notice one would be this way, which is the mesoform. The other one will be like this, and then the next will be mirror image of the same, like this. So these are the 3 forms which I can get. So basically here I can count it as 3, 1, 1, 1, and 1. So total we can have it as 7. But if you have put it structurally, I'll give the answer correct for C also. Okay. Considering if there is structure only, ask if that was the answer which you have marked, I'll make it correct as well. Okay. I'll change that. Next. Select the following pairs here, A, B, C, D. Select the following pairs. Yeah, correct. Sorry, correct pairs we need to select. So first one we have, are these chain isomers or not? So check out 1, 2, 3 carbons. Here we have one, two, three carbons. So this is not a chain isomer, correct? It is simply a positional form. Next, these two are chain isomers. See, one, two, three, four, five carbons. One, two, three, four. Four carbons here. So yes, this side, if you compare here, it is definitely appearing to be the chain isomer here because the length of the chain is different. While here, if you compare, I put bromine here and chlorine here, so that changes the substituent as well. So this is not chain isomer. These are metamers, correct? Because we have change in the alkyl group on both sides. Next, sorry. Are these metamers? No, these are not metamers. Okay, because number of carbons, if you compare here on the left, here also we have the same group. Here also we have the same group. So we didn't change anything. So these two are identical. Next, anti form is the most stable ethane form. Is it anti or gauche? It is the gauche, right? Because if you have two OH groups like this, we have OH and OH here. So there will be hydrogen bonding at this location. So gauche is more stable. Hence, even this is not correct. So only B is correct in this case. I guess that is clear, everybody. Next. Newman projection representation, if you compare between C2 and C3, okay? C2 and C3 means first you need to figure out what is the length of the chain here. So 1, 2, 3, 4, 5. Basically, this ethyl I can write it as 1, 2, then we have 1, 2, 3. Oh, one extra carbon I put. So 1, 2, 3, 4, 5. Yeah. So 1, 2, 3, 4, 5. And on the third position, I have a CH3 group. And I need to make it between C2 to C3 here. So how would I make it here? So let's suppose if you have two hydrogens here. Two hydrogens means I'm talking about the carbon 2 position here. So here we have two hydrogens, then the other one has to be methyl. And on the back side, if you compare, we have one methyl, one ethyl, and one hydrogen. So here hydrogen is already given, methyl is already given, so it has to be ethyl. So here this is Y and this is X. So X is methyl, Y is ethyl. So our option A is correct. Everybody clear? Which of the following compound will show tautomerism? Okay. The first one definitely shows tautomerism. What kind of tautomerism? Let me show you here. We can have this as a phenolic group with N double bond O. And when the hydrogen shifts here, that becomes an oxime form. Okay. That will become quinoxime. Right. So yes. So first one will show the tautomerism here. Here there is no hydrogen on this end, so no tautomerism. This is at a bridge position where this side there is no hydrogen. Even though this side hydrogen, it is at a bridge position, cannot be used. Here there is no hydrogen, so I cannot tautomerize. So only A is correct option. The dihedral angle between methyl group in cis and trans 1,2-dimethyl cyclopropane is okay. So 1,2-dimethyl cyclopropane. Cyclopropane is like this here, and here I have 1,2-dimethyl. I have a methyl here, and I have a methyl here, like this. Got it? Now, what is the problem here? What is the problem you will see here is like this. So if at all I take this as a front carbon and this as a back carbon here, so I would have front carbon like this, and on the front carbon, one carbon is going this way and one hydrogen will be here, one methyl will be here like this. Okay. And on the back carbon, if you notice, methyl would be here only because this group will connect here and hydrogen will be here like this. Clear now? This is how the connection would be. So if you draw the Newman projection for this one, this is how it looks like. Okay. So the dihedral angle between methyl groups in cis and trans position. Okay. Now when you have cis position, you can have methyl here and methyl here. So that makes it 0 degrees. And when you have it in the trans position, same structure, but instead of hydrogen and methyl, I can replace that hydrogen here and methyl here. So now you can notice what is the angle that it is making, 120 degrees. Here, what is the angle that is making, 0 degrees. So what are the angles that it will show? It will show 0 degrees and 120 degrees. Clear? Next. Major tautomeric form of this one. See, I can push this hydrogen towards this oxygen, and that way I can make it into double bond form here, double bond here, and OH. Okay, this is the way I can keep it. Clear? This is one way I can make the tautomerism. Another way, can I use this hydrogen? Yes, I can use that hydrogen also. I can use this hydrogen instead. I'll keep this hydrogen this way. And if at all I make this hydrogen to push all the way here, I can push this double bond here, I can push this double bond here. So double bond, and OH this way. Correct? If I keep it like this, is there any advantage I'm getting? Yes, indeed. What is the advantage here is you can see there is a lone pair. That lone pair can make a conjugation and make the ring aromatic. So this one is more appropriate. Okay, clear? Right. So there is a key change here. I think it was answer given was A. I have to change it to C. I'll change that. Okay. Next. Functional isomer of this here for this case is, now obviously here there is something missing. It should have been a triple bond. I'm sure you should have understood by that, because carbon cannot have only two bonds here. It has to be a triple bonded here. That means the DOU for this is 2. Okay. If the degree of unsaturation is 2, check out in which option the degree of unsaturation is 2 in the given cases. Here it is 2, here it is 3, here it is 2, and here it is 2, and here it is also 2. Okay, clear? So functional isomer of this one. Uh, yeah, we bonded. Okay. Now notice this one, everybody. In this case, actually, if you notice A, C, D, all appears to be functional isomer. But I told you, whenever you have a straight chain and whenever you have a cyclic chain, we have a different name for it. That is ring chain isomerism. So if you are comparing between this and this, use the terminology RCI. This and this also RCI. Okay. But if you are comparing that with these two, then this is a triple bonded form, this is a double bonded form. Hence, these two are functional isomers. So go with A in this case. Okay. Next. If you compare these two here, we have an acid here, but this is peroxy acid. This is a normal acid. Okay, one is a peroxy acid, the other one is a normal acid. In that case, what do we have? But these two acids are not the same. These two are two different types of acids. So since these two are two different types of acid, they will become functional isomers. Got it? Here. Okay. Next. Next. Check out on the 10th one here. So if you compare this, the alkyl group here has basically cyclohexide, and here we have an ester form, while here also it is an ester form. If you notice carefully, C double bond O, O, like this and like this. Okay, so this is also an ester, this is also an ester, only there is a difference in the alkyl groups. If you have difference only in the alkyl groups but yet they are retain the same functional group, we call them as metamers. Guys, clear? It's a very important case. It's a metamerism which is happening in this case. Okay. Next. In which of the following compounds enolic content will be maximum? Okay. Earlier I told you if you have an ester form, the enol content decreases. Here both sides we have ester, right? Here we have ketone. Here we have ketonic form, correct? And most importantly, here in this ketone, there is a help that will offer, because if you have a double bond O and H here, double bond O and CH3 here, first they will have a hydrogen bonding. Along with that, there is an extended conjugation that can be offered even from benzene also. Just a minute. Close. We can get an extended conjugation from both the ends that makes this to be having more enolic form. Sorry. Next, 12th one. The most stable conformation among the following is, okay. Now, here, if you notice that this is axial and axial, here it is equatorial and axial, here it is axial and equatorial, here it is equatorial and equatorial. Okay. If you may recall, the bulky group should be always placed on the equatorial position to minimize the diaxial repulsions. Hence, D will be most stable form. Why? This will have least diaxial repulsions. This will have least diaxial repulsions, everybody. Identify the total structural isomers of C6H11 with a molecular formula here. Got it? So, how many we can have? Degree of unsaturation, if you notice, degree of unsaturation, if you notice, we have C6H12, that is 0, which means you need to keep it in a straight chain only. So let's see, we will put everything in a straight chain form. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Next, we start with 5. So I can put push methyl here. I can push methyl here. These two are the next forms here. Next with 4. 4, I can have 2 methyls here and 2 methyls like this. Okay. Other than that, we cannot bring more number of alkyl groups here. So this is the maximum number of isomers which you can make it. So how many we got? 5 of them. Okay, we got 5. So I hope all of you got this point. Next. Identify total number of possible ethers excluding stereoisomers here, C4H10O. Again, if you may notice, the degree of unsaturation in this case is 0. Okay. And you need to make ethers out of it. So let us make it into straight chain form here. First, this is one ether. This is one ether. This is another ether. Correct? This is the maximum number of ethers that you can get. You cannot get any other straight chain ethers out of it. So maximum, how many we got? 3. Okay. Next. Notice the 15th one. 1,2-dichloroethane. Okay. Next. Check out 15th one. It is making an anti-conformation. Okay. So I need to check which are the options are more appropriate. Correct. So if it is option A, whether it is matching with what are the codes here, A, B, C, D, which of them are matching. Let's see one by one. So these are the codes, everybody. You can notice that 1,2-dichloroethane. So basically we have like this 2 chlorines here. This is 1,2-dichloroethane. Okay. So let me put all the conformations first, everybody. So first I can have chlorine here, chlorine here. This is the first anti-conformation. Next I can have chlorine here, which is the gauche conformation. Next we have eclipsed conformation chlorine and chlorine here like this. Next, we have partially eclipsed conformation where chlorine is here and rest of them are hydrogens like this. These are the conformations we have. So we have this as anti, gauche, eclipsed, and partially eclipsed. Okay, so let's start with the first one. If you have an anti-conformation has non-zero dipole moment, incorrect. Okay, it will not have non-zero dipole moment, it will have zero dipole moment. Clear? Actually, this was little confusing. Maybe it should have been 1, 2, 3, 4. Correct? But based on the options, you might have understood that that is what we are looking into. Okay. So check out first. Does it have more stable conformation? Yes, indeed. So in the case of chlorine, anti is the most stable, then gauche, then partially eclipsed, then eclipsed. So for P, I can say 2 is a match. Hmm? Next, having C2 axis of symmetry. Does it have a C2 axis of symmetry? Indeed. In fact, if you take this as the axis and rotate it around, so this chlorine will be repeated. You can see here also like this. So suppose if at all I put an axis here, this chlorine, if it goes here, comes here. So it can have on the anti-form. This is the anti-form you can see. From here, if at all I keep it like this and rotate it around, you will get the same chlorine repeated after 180 degrees, which means it has a C2 axis of symmetry. So 3 is also correct for it. Having a plane of symmetry, yes, indeed, this itself can act like a plane of symmetry here. Correct? Everybody here? So there is a plane of symmetry as well. So does it have plane of symmetry? Answer is yes. Next, Gauss conformation. It will have a non-zero dipole moment. Yes, that is correct. Most stable, no. Does it have a C2 axis of symmetry? Okay. If this is the Gauss form here, does it have a C2 axis of symmetry? Well, I think we can have it like this. If you have an axis drawn from here, this chlorine can be repeated after 180 degrees again. So yes, it can have C2 axis of symmetry. Correct? Does it have a plane of symmetry? No, it does not have any plane of symmetry. You draw from here, 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 any direction. There is no plane of symmetry here. Okay. Next, if it comes to eclipsed conformation, in the case of eclipsed conformation, this one is the conformation here. Does it have non-zero? Answer is yes. It still have non-zero conformation here. Correct. Next, is it more stable? No. Does it have C2 axis of symmetry? Yes, indeed. The axis which is passing through it, it can repeat the chlorine on the same direction again. So yes, it can have C2 axis of symmetry. Okay. Does it have a plane of symmetry? Yes, indeed. It has a plane of symmetry here. Got it? Because you can see directly this plane itself can act like a plane of symmetry in this case. Next, partially eclipsed form. So first one is again correct because there is a non-zero dipole moment. Okay. Does it have C2 axis of symmetry? Yes. Here, if at all I put a axis, you can see the chlorine and chlorine repeats after 180 degrees. So yes, it will have C2 axis of symmetry. Does it have a plane of symmetry here? Okay. Now, if you notice the plane of symmetry, I cannot put this as a plane of symmetry here. Reason being, these are, distributed like this. Here, this way, and like this. And one chlorine is here, one chlorine is here. So this cannot have any plane of symmetry in this case. Clear, everybody? So therefore, in this position, we cannot have it. Now notice which of the following codes will make a correct match out of that. 2, 3, 4, 1, 3, 1, 3, 4, and 1, 3. 2, 3, 4, 1, 3, 1, 3, 4, and oh, this is not given 1, 3. No, okay, only D is the one which is given like that. So D is a correct code. Okay, about 16th. For how many structural isomers are possible? For this, how many structural isomers are possible when one of the hydrogen is replaced by chlorine? Okay, One of the hydrogen is replaced by chlorine. Okay, so let's see. One position is this one. Okay, this is one position. Second position, third position, fourth position. Correct? So these are the only four positions we can have where other positions are repetitive. So how many we can get? Only four. Four different groups, four different structural isomers. How many structural isomers are possible for C3H6BrCl? Here you can clearly notice the degree of unsaturation is zero, which means it has to be straight chain. So we'll start from here like this. I'll put chlorine, bromine together. Next, I can put chlorine, bromine here. I can put chlorine and bromine opposite to that. And I can also put chlorine and bromine at the middle like this. Correct? These are the forms which I can have. Okay. Now, is there more forms which I can get here? Okay. No, this is the maximum forms which I can get. So how many we can have here now? So check out. We can have one, one, two, three, four. I think I should get one more form. Maybe I'm forgetting something. Sorry. This is not bromine. This is chlorine. So I'll have one more form like this. Chlorine. Yeah. Bromine in the middle and chlorine in the chlorine outside. Like, so how many we got? Five of them. Please check. Ah, next. How many amides are possible with this case? Now, degree of unsaturation is 1 in this case. You can calculate and see, right? So 5 minus 9 plus 1 by 2. So that makes it 1. So degree of unsaturation is 1. So let us start with single hydrogen, okay? So like this, H, C double bond O, N, and 3 carbons we have. So 3 carbons, I can keep it like this. This is, sorry, for straight chain, like this. Then I can keep it as N with isopropyl form, and then I can have N with one methyl here and then ethyl here like this. This is the form I can keep it. Okay. And another form I can keep it here is double bond O, N with three methyls. Sorry, you cannot have three methyls, only two connections we can have. So only this many. Next, we'll add with one methyl group on the left hand side. So that means methyl. So there are two more carbons left. So one way is I can have an ethyl like this. Other form is I can have two methyl like this. This is one way. The third one is I can have three carbons on the left here and then nitrogen NH with one methyl group on it. Nitrogen with one methyl group on it. So this is one form. Or I can have four of it. I cannot have four of it. That's it. These are the forms I can have maximum. Clear? So notice how many we are getting in this case now. So I got is there anything I missed out? Amides. Yeah. I can get a primary form of amide also. Sorry. So I can get 1, 2, 3, 4. 4 double bond O NH2. And this 4 can be written as 3 double bond O NH2 like this. These are the two forms I can get. Yeah. Is there anything else I can get? No, that's it. Yeah. So count how many we got totally. So 1, 2, 3, 4, 5, 6, 7, 8. So total we got it as 8. Please check if anybody has a doubt on that. I hope all of you got these 8 forms. Next. Which of the following is not isomer of 2,2-dimethyl pentane? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry. 2,2-dimethyl pentane. So this is the pentane form we have, which means you just simply count with the number of carbons here. And my suggestion is check out for option A, B, C, D by drawing it. First hexane. So we have 1, 2, 3, 4, 5, 6. and 2-methyl hexane like this. Correct? This is the one we have. Okay. Next. So, which means if you take 2,2-dimethyl pentane, number of carbons will be 1, 2, 3, 4, 5, 6, 7. Here also we have 1, 2, 3, 4, 5, 6, 7. Okay. So there is no problem in both the cases. So first one is matching. So 2-methyl hexane. Second one, 2,3-dimethyl pentane. Okay. So same pentane, 2, 3. So that is also matching. 2,3-dimethyl butane. So butane means one carbon is left. And last one, heptane. So 1, 2, 3, 4, 5, 6, 7. In fact, we have 7 carbons only. So only one which is not matching is this one. So which is option 3. Okay. Next one. Uh-oh. This 20th question is missing, I guess. Okay. So that was a mistake from my end. Yeah. There is 20th question missing out there. So I'll change that marks accordingly. Next, check out 21. The number of functional groups present in the following compound is, okay? See how many functional groups are present in this case. The number of functional group present in the following. Okay. So you need to check out all the sides here. So starting with here, this is an aldehyde. I'll keep writing that as aldehyde. Next, it is a 1-degree amine. Okay. Amine. Okay. Then this is a ketone. So this is ketone. Next, this is an amide. It is a different functional group, which is amide. Next, this is an anhydride. If you notice that, this is an anhydride. Anhydride. And lastly, this is an acid. It is an acid group. So how many total we got? 1, 2, 3, 4, 5, 6. 6. So we should have a total of 6 functional groups in this. Clear? Let's see. Next one. Which of the following compound is named correctly according to IUPAC convention? What would be the sum of the positions of two chlorines? Okay. So now notice, obviously ketones has to be given the high priority. So we start with 1, 2, 3, 4, 5, 6. So you might think, sir, why don't we start from here? 1, 2, 3, 4, 5. Can you see the chlorine is coming at 5 and 6? So that means it is coming at a higher locant. So that is not correct. So this is a correct one. So what is the position of chlorines here? 4 plus 5. So which makes it 9. Done. I guess this part is clear. Next. Check out. Number of primary amines for the molecular formula C4H11 and N23. We need to check only primary amines. So start with 4 carbons here. So 1, 2, 3, 4 with NH2 and keep changing that position of amine. Another one is NH2 here. Now put 3 carbons. So 3 carbons with primary amine like this. 3 carbon, I mean like this, 4 carbons, but primary amine here. This one. Correct? So how many we got total? These are the only primary amines we can get. So 1, 2, 3, 4. So answer is 4. Next. Check out on 24th. How many cyclic isomers of C5H10 are possible? Okay, C5H10. C5H10 are possible here. Got it? Here, I think the question was more appropriate. This, we have solved it already. We had a similar question. We got it as 5. Okay. Next. How many benzonoid positional isomers are possible for C8H10? So basically, we need to have benzonoid. Okay. So here, like this. And what did he ask? Benzonoid positional isomers. Acha. If you want positional isomers, that means the only way possible is having two same groups. That is only possible when you have methyl and methyl here like this. So these two, then CH3, CH3. Now you can see positional changes only. And here we have CH3 positional changes. So only positional base changes, how many we find? Three of them. That's it. So how many total number of benzenoid isomers we got? Three. Everybody clear? So I think two corrections we had in the question. Along with that, one is a bonus. That question was missing out, 28th question. Otherwise, this was the paper. Yes, Samir. Now you can ask.
Sir, can you go to 22nd question?
Yes, Bacha. Yes, please.
Yes, sir, why didn't we start from that O, that upper
Uh,
one?
if you start with that O here, one, two, three, this numbering is same. But here you are getting chlorines at 5 and 6.
And what if we go clockwise?
If you go clockwise, you're getting at 4 and 5.
No,
Correct?
clockwise from that O, upper O. We
From
will get
here,
from
like this.
this side.
But ketones are functional groups. Now, beta, that should be high priority.
Okay,
They
sir.
should first get at the lowest locants. So either you have to go like this or you have to go like this.
Okay, sir.
Okay. People, anybody else has a doubt in the paper, any question, please do ask right away.